settle into the Sleepy Mind channel, where tonight we explore one of the most familiar substances on Earth, and a mystery so enormous that it has been developing for billions of years. Imagine for a moment that we could remove all the salt dissolved in every ocean on Earth and spread it evenly across the land. There would be enough salt to cover the continents with a layer roughly 500 feet deep. It is an extraordinary amount, hidden so completely within the water that when we stand beside the sea, we see only waves stretching toward the horizon. Nearly 97% of all the water on our planet is contained within the oceans, and almost every drop of it carries dissolved salts. Yet much of the water continually arriving at the sea is fresh. Rain falls fresh from the sky. Snow gathers on mountains and eventually melts. Streams flow into rivers, and rivers pour fresh water into the ocean every moment of every day. At the same time, warmth from the sun lifts enormous quantities of water from the surface of the sea and carries it invisibly into the atmosphere, where it eventually returns as fresh rain. Water arrives, water leaves, and rain falls again, yet the salt remains behind. This cycle has continued across an almost unimaginable span of time, which leaves us with a surprisingly difficult question. How did nearly all of Earth's water become salty in the first place? That question hides an even stranger mystery. If minerals have been entering the oceans for billions of years, why have the seas not simply become saltier and saltier without end? Somewhere within this enormous planetary system, substances must not only be entering the ocean, but leaving it as well. Some of the processes responsible are happening in places we rarely see, within rocks on distant mountains, inside the bodies of tiny marine organisms, beneath layers of sediment, and along the ocean floor where seawater encounters the rocky crust of the Earth. Even the saltiness of the sea is not the same everywhere. Rain, rivers, evaporation, freezing ice, melting ice, and enormous ocean currents can all change the concentration of salt from one region to another. And those differences matter because the salt dissolved in seawater helps influence its density and movement, connecting the simple question to ocean currents, climate, marine life, and the history of our planet itself. The answer begins long before the first human ever tasted seawater, and even before the first ocean existed. To understand why a drop of seawater tastes salty today, we have to travel billions of years into the past, to a young Earth with no familiar beaches, no winding rivers, and no great blue seas. If you're listening to this as you drift towards sleep, I'm really glad you're here with me. If you enjoy these journeys, please like the video and subscribe to the Sleepy Mind channel. It truly helps me keep creating new sleepy stories like these every other day. For all night listening, check out the playlists on a variety of interesting topics like nature, space, the human body, history, and more, all ready to carry you through the night. Tonight, we are going to follow the story of the ocean from a time when there was no ocean at all. We will watch as a fiery young planet gradually changed, as water gathered in its atmosphere, and as cooling conditions eventually allowed that water to return to the surface. Later, we will follow rain across ancient rocks and discover how something as gentle as falling water could slowly begin changing the chemistry of the future seas. We will follow minerals from mountains into streams, from streams into rivers, and from rivers into the ocean. We will eventually travel beneath the waves to places where seawater interacts with the crust below, and we will discover that the ocean is not merely collecting material, but constantly exchanging it with the planet around it. What begins as a question about the taste of seawater will carry us through volcanoes, ancient rainstorms, changing continents, ocean currents, marine life, and billions of years of Earth history. So make yourself comfortable and allow the details of the day to gently fade into the background. Our journey begins on a world so ancient and unfamiliar that almost nothing around us would have looked the way it does now. Let us begin. Earth formed approximately 4.54 billion years ago, although there was no single instant when a finished planet suddenly appeared in space. Instead, the young Earth grew as material surrounding the newly formed Sun gradually came together under the influence of gravity. Tiny grains became larger pieces collided and combined, and over immense stretches of time, a growing world emerged. Some collisions were relatively small, while others involved enormous bodies capable of releasing extraordinary amounts of energy. With each major impact, tremendous heat could be generated. Radioactive elements within the young planet also released heat, and dense materials moved toward the interior as Earth began separating into layers. The world taking shape was nothing like the calm blue sphere we see in photographs today. There were no forests covering the land, no animals moving across the surface, and no oceans reflecting clouds above them. The familiar Earth was still billions of years away, and the planet was passing through one of the most violent chapters in its entire history. The young Earth was intensely hot, and large portions of its rocky material were molten during its earliest history. Heat came from several sources, including the collisions involved in building the planet, the movement of dense material toward its interior, and the decay of radioactive elements. Enormous impacts could melt great regions of the surface, while material from deep within Earth continued to rise and cool. The planet was slowly organizing itself. Dense metals, particularly iron and nickel, moved inward and contributed to the formation of the core, while lighter rocky materials remained closer to the surface. Above them, the outer portions of the planet gradually began losing heat to space. Solid crust could form, only to be disrupted again by impacts and intense geological activity. Volcanoes released material from the interior, molten rock spread across parts of the surface, and the landscape continually changed. If we could somehow have watched this process while remaining safely above it, there would have been no peaceful coastline to follow with our eyes. We would instead have seen a restless young world still becoming the planet that would one day support oceans and life. The atmosphere above this young Earth would have been equally unfamiliar. Earth's earliest atmosphere contained almost no free oxygen compared with the air surrounding us today. There were no forests producing oxygen, no grasses covering plains, and no complex plants at all. In fact, the biological processes that would eventually transform Earth's atmosphere had not yet developed. The gases surrounding the planet were shaped largely by geological activity. Volcanoes and the hot interior released gases that contributed to the evolving atmosphere, including carbon dioxide, nitrogen, water vapor, and sulfur-containing gases. To a modern human, this atmosphere would have been completely unbreathable. Yet hidden within that hostile mixture was something essential to the world that would eventually emerge. Water was present, not as the vast liquid oceans we recognize today, but in significant amounts as water vapor released into the atmosphere. Volcanic activity helped deliver enormous quantities of water vapor from Earth's interior into the atmosphere. We usually think of volcanoes in terms of lava, glowing rock, ash, smoke, and destruction. So the idea that they could be connected to the formation of oceans may seem surprising. But magma contains dissolved gases, including water. As magma rises toward the surface and pressure decreases, those gases can escape. Modern volcanoes still release large quantities of water vapor, and on the young Earth, volcanic activity was a major part of a much more geologically active world. Eruption after eruption released gases into the atmosphere, including the water vapor that would become part of Earth's developing water cycle. Water associated with the materials from which Earth formed also contributed to the planet's supply, and the complete history of Earth's water is complex, but the important part of our story is that enormous quantities of water eventually existed above the surface as vapor. The future oceans were beginning to take shape, even though much of their water was not yet resting upon the ground as liquid. As Earth gradually cooled, conditions began to change. Heat continued escaping into space, the outer crust became increasingly stable, and temperatures eventually allowed water vapor in the atmosphere to condense. Invisible vapor could form tiny liquid droplets. Clouds could gather above the young landscape, and water could begin falling toward the surface. It is difficult to imagine what those ancient skies might have looked like, because almost everything about the world below them was different from the Earth we know. There were no trees bending beneath the rain, and no rivers already waiting to receive it. Water fell upon bare rock and volcanic terrain, gathering wherever the shape of the surface allowed it to remain. This transition from vapor to liquid water was one of the most important changes in the history of our planet, because once liquid water could persist at the surface, an entirely new set of processes became possible. Water could collect, it could flow, it could interact with rock, and eventually, it could begin filling the great low areas of the young planet. As the young Earth continued to cool, the water gathering in its atmosphere could return to the surface again and again. Rain became part of a cycle that would eventually transform the appearance of the entire planet. The exact conditions of this distant period are difficult to reconstruct, and the development of Earth's oceans was more complicated than a single uninterrupted storm, but across immense spans of early Earth history, enormous quantities of water moved from the atmosphere to the surface. Imagine rain falling onto a world without trees, grass, animals, roads, buildings, or any of the familiar features that now soften the landscape. It struck exposed rock, flowed across volcanic terrain, gathered in depressions, and returned again as the atmosphere and surface exchanged water. In some places, water would have encountered hot ground and evaporated again. Elsewhere, as conditions became cooler and more stable, liquid water could remain. Over millions of years, repeated rainfall and the movement of water across the surface helped fill the lowest regions of the young planet. The world was slowly acquiring something that would eventually become one of its most recognizable features. Great bodies of liquid water were beginning to endure. These early waters collected wherever the shape of Earth's surface allowed them to gather. Gravity drew flowing water toward lower elevations, just as it does today, and depressions within the young crust became natural places for water to accumulate. Over time, these low regions developed into the earliest ocean basins. They would not have looked exactly like the Atlantic, Pacific, Indian, Arctic, or Southern Oceans that appear on a modern map, because the crust beneath them and the continents surrounding them were still changing. Earth's surface has never remained fixed. Rock is created, altered, moved, buried, and recycled, while the great plates, making up the outer portion of the planet, slowly shift. The ocean basins of the distant past have therefore been reshaped many times, yet the basic process was already underway. Water falling from the atmosphere moved toward low ground, accumulated there, and formed increasingly large bodies of liquid water. Drop by drop and storm by storm, a planet that had once possessed no familiar ocean began becoming a water world. The earliest oceans would have been chemically different from the seas we know today, and in the beginning, they would have contained far less of the dissolved salt that now gives seawater its familiar taste. The water arriving from the atmosphere did not fall as the equivalent of modern seawater. Its chemistry was influenced by the gases around it and by everything it encountered after reaching the surface, but the enormous accumulation of salts found in today's oceans had not yet taken place. That distinction brings us directly to the mystery at the center of our journey. The ocean did not need to begin as a vast reservoir already containing its modern concentration of salt. Instead, its chemistry could change as water interacted with the solid earth around it. The young seas were in contact with rock, volcanic material, gases, and an active crust, and every one of those interactions had the potential to alter what was dissolved in the water. The saltiness familiar to us today would emerge through processes operating repeatedly across geological time. While water was gathering into early oceans, the solid surface of Earth was also continuing to evolve. The first continental crust gradually developed, and portions of it rose above the surrounding water. These early land areas were not the continents we would recognize from a globe today. There was no North America with its familiar outline, no Africa stretching across the equator, and no Australia isolated in the southern seas. Continents themselves have long histories. They grow, break apart, collide, and are rearranged by the slow movement of Earth's outer plates. Some ancient pieces of continental crust have survived within modern continents, preserving fragments of a world that otherwise disappeared long ago. As more stable regions of continental crust emerged above the water, Earth gained expanses of exposed rock that could interact directly with the atmosphere and with falling rain. That meeting between water and stone would prove enormously important to the future chemistry of the oceans. A bare rock may appear permanent when viewed across a human lifetime. Mountains seem solid, cliffs seem immovable, and a stone lying beside a river may appear almost unchanged from one year to the next. But geological time changes our sense of what is permanent. Give water thousands, millions, and eventually billions of years to interact with rock, and even the hardest landscapes can be transformed. The rain falling upon Earth's first exposed land did not merely touch the surface and flow away without consequence. It began wearing away the rock. Some of that change was physical. Water could move loose particles, carry fragments downhill, and help reshape rough surfaces. Temperature changes, flowing water, and other natural processes could gradually break larger pieces into smaller ones. But another transformation was occurring at a scale too small for anyone to see directly. Water was interacting chemically with the minerals inside the rock itself. This is where the story of salty oceans begins to become particularly interesting, because a river does not need to look salty to carry the ingredients that can eventually contribute to the chemistry of the sea. Clear water flowing across stone can contain dissolved substances that are completely invisible to the eye. Even today, water that looks perfectly clean may contain calcium, sodium, magnesium, potassium, and many other dissolved ions, derived partly from the rocks and soils it has encountered. The concentrations in rivers are generally far lower than those in seawater, which is why ordinary river water does not taste like the ocean. But the difference between a little and a lot becomes important when the process continues across nearly the entire planet for immense periods of time. A tiny quantity carried by one stream may seem insignificant. Countless streams and rivers delivering dissolved material year after year are something very different. The earliest exposed continents therefore became more than pieces of land rising above the sea. They became enormous surfaces upon which water and rock could continually interact. Rain struck the ground, traveled across stone, entered cracks, collected into channels, and eventually found its way toward lower elevations. Every journey created another opportunity for water to encounter the minerals locked within Earth's crust. The rocks themselves were composed of many different chemical ingredients, assembled into minerals under conditions that might have existed deep underground, within cooling magma, or during earlier geological events. Once those minerals were exposed at the surface, they entered an environment very different from the one in which some of them had formed. They encountered water, atmospheric gases, changing temperatures, and a constantly shifting landscape. Slowly, the surface of the continents began to weather. For now, however, we can remain on those ancient landscapes and imagine the quiet beginning of the process. Above us, clouds carry water across a young planet. Rain falls onto newly exposed continental rock and begins flowing downhill. Beneath that water are minerals that have been locked within stone, perhaps for millions of years. Yet the arrival of rain has begun changing their surroundings. The water does not need to be powerful enough to smash a mountain apart. It only needs time, chemistry, and countless repetitions of the same seemingly insignificant interaction. Drop after drop, storm after storm, exposed rock begins to change, and water carries traces of that change away with it. The first oceans have formed, the earliest continents have risen above them, and the connection between the two is becoming stronger with every rainfall. But there is still one important part of the process we have not examined. Ordinary rainwater is not chemically neutral in the way we might imagine. As it moves through the atmosphere, it acquires something that makes it slightly better at attacking rock. And that quiet chemical change will help unlock the minerals that have been waiting within the continents. The ingredient that gives rainwater this quiet ability to change rock is something that surrounds us today and was also present in the atmosphere of the early Earth. As rain falls through the air, the water naturally absorbs some carbon dioxide. Additional carbon dioxide can also enter water after it reaches the ground, especially in the modern world, as water passes through soils where living organisms and decaying organic material release the gas. Once carbon dioxide dissolves in water, a small portion reacts with the water to form carbonic acid. The name may sound dramatic, but this is not the kind of powerful acid that immediately burns through solid material. Carbonic acid in ordinary rainwater is weak, and its effects can be extraordinarily slow. Yet geological history provides it with something far more powerful than strength. It provides time. A weak chemical reaction repeated across countless storms over thousands and millions of years can alter landscapes, dissolve minerals, and help carry some of the chemical ingredients of solid rock toward the sea. This means that a drop of rain is slightly different after interacting with carbon dioxide than we might imagine from simply looking at it. It remains clear and appears completely ordinary, but its chemistry allows it to react with certain minerals in rock. As rainwater moves across exposed surfaces and seeps into tiny cracks, these reactions begin altering the minerals it encounters. Some minerals are more resistant than others, while some are gradually transformed into new materials or release dissolved ions into the passing water. The process is slow enough to be invisible from one moment to the next. We cannot stand beside a mountain during a rainstorm and watch its minerals disappear before our eyes. But the mountain does not experience time as we do. Human beings measure lives in decades, while landscapes can remain exposed to weathering for millions of years. What appears permanent to us can therefore be continually changing on the much longer clock of the planet. This slow alteration of rock through chemical reactions is known as chemical weathering, and it is one of the great links between the continents and the oceans. Chemical weathering is different from simply breaking a rock into smaller pieces. A stone can crack into two pieces and still contain essentially the same minerals it contained before. Chemical weathering actually changes minerals or dissolves components from them. Water, carbon dioxide, and other substances can react with exposed rock, allowing certain elements to enter the water in dissolved form. Some rocks respond particularly noticeably to weakly acidic water. Limestone, for example, contains minerals that can gradually dissolve as water moves through cracks and openings. Given enough time, this process can contribute to the creation of caves and other remarkable landscapes. Other types of rock weather in different ways, but the larger principle remains the same. Water moving across and through the crust is not merely passing over an unchanging surface. It is participating in chemical reactions with the planet itself. As rocks undergo chemical weathering, minerals release dissolved substances into the surrounding water. These substances do not necessarily resemble the crystals or grains we normally picture when we hear the word salt. In water, many dissolved compounds separate into charged particles known as ions. Sodium can exist as a dissolved ion. Calcium, magnesium, and potassium can do the same, along with many other substances. Because these particles are dissolved, they can travel with water without making it appear cloudy or visibly different. A stream can look perfectly clear while carrying an invisible collection of dissolved material from the rocks within its drainage area. This happens throughout the world today, just as related processes operated across ancient landscapes. Every time water moves through weathered rock, soil, underground formations, or river channels, its chemistry can change slightly. By the time that water reaches the sea, it may carry a chemical record of some of the landscapes through which it has traveled. Once released from rocks, these dissolved minerals begin a journey governed largely by gravity and the movement of water. Tiny streams gather water from slopes and valleys, carrying dissolved material with them. Those streams join other streams, creating larger channels that continue downhill. Eventually, many of these channels become rivers. A river is therefore much more than a moving ribbon of water. It is also a transport system connecting the interior of a continent with the ocean. It may carry visible sediments such as sand, silt, and clay, but it also carries substances that cannot be seen. A glass of river water can appear clear while containing dissolved ions gathered from an enormous area of land. Some may have entered the water only recently. Others may have traveled through groundwater before reaching the river. Together, these countless small contributions become part of a continuous flow of dissolved material toward lower elevations. Rivers then carry these dissolved minerals toward the oceans, sometimes across extraordinary distances. A raindrop that falls far inland may become part of a stream, then a river, and eventually reach a coastline hundreds or thousands of miles away. During that journey, the water may pass through different types of rock, receive water from tributaries, move through lakes, enter underground pathways, and return to the surface again. Each region can contribute its own mixture of dissolved substances. When the river finally reaches the sea, its water joins an ocean containing material delivered by countless other rivers from across the planet. One river alone would not explain the enormous quantity of dissolved salts in seawater, but the process is not occurring in one river, and it has not been operating for only 1 year. Rivers across the world have been carrying dissolved material from the continents toward the oceans over immense spans of geological time. Among the elements carried in dissolved form, sodium became one of the most abundant in seawater. Sodium is naturally present in many minerals within Earth's crust, and weathering can release sodium ions that eventually enter streams, groundwater, and rivers. Once sodium reaches the ocean, its behavior becomes especially important because it can remain dissolved for a very long time, compared with many other substances. Some elements entering seawater are removed relatively quickly through biological activity, chemical reactions, or incorporation into sediments. Sodium can remain in solution much longer, allowing large quantities to exist within the ocean at any given time. This helps explain why sodium is such a prominent part of modern seawater chemistry. But sodium by itself is not the substance we recognize as ordinary table salt. For that familiar compound to form, another important ion must be present as well. That other major ingredient is chloride. Chloride in the oceans has origins connected to Earth's long geological history, including volcanic gases and interactions involving rocks and water. Volcanic activity released chlorine containing compounds from Earth's interior, while geological processes involving the crust also contributed to the chemical inventory of the oceans. Once present in water, chloride can remain dissolved for very long periods, much like sodium. This persistence matters because the ocean is continually receiving substances while also removing them at very different rates. A substance that remains dissolved for a long time can become abundant, even when its arrival is gradual. Across the history of the oceans, sodium and chloride became the two dominant dissolved ions in seawater, creating the chemical partnership most familiar to us whenever we taste salt. When sodium and chloride are brought together in the familiar solid form, they create sodium chloride, the substance we know as common salt. In seawater, however, we should not imagine countless microscopic cubes of table salt simply floating between water molecules. The sodium and chloride are largely present as separate dissolved ions surrounded by water molecules. If seawater is allowed to evaporate and enough water disappears, those ions can eventually come together into solid salt crystals. This is why salt can be harvested from seawater through evaporation, a process humans learned to use thousands of years ago. But within the open ocean, the salt remains overwhelmingly dissolved, invisible within the water, even though there is enough of it to give the sea its unmistakable taste. The next clue is hidden in a process so familiar that we see its effects whenever a puddle disappears after the rain. Water can leave. The minerals dissolved within it often cannot leave in the same way. Across the surface of the world's oceans, warmth from the sun continually allows liquid water to become water vapor and enter the atmosphere. That water will eventually return to Earth through the water cycle. But the dissolved salt does not simply rise into the sky beside it. The distinction between what leaves the ocean and what stays behind is one of the most important parts of our story, because it explains how tiny quantities of dissolved material delivered by fresh water can gradually become concentrated within an enormous salty sea. And even today, every river flowing toward the coast continues participating in that ancient process. Once river water enters the ocean, however, its journey takes an important turn. The water itself does not necessarily remain in the sea. Every day, enormous quantities of ocean water are warmed by energy from the sun. Molecules near the surface can gain enough energy to escape the liquid and enter the atmosphere as water vapor. This process is evaporation, and it occurs across the world's oceans continuously. We cannot normally see the water vapor leaving the sea because individual molecules are invisible, yet the scale of the process is immense. The oceans provide most of the water that enters the atmosphere through evaporation, helping create the clouds and precipitation that sustain the global water cycle. A molecule of water near the ocean surface may eventually rise into the air, travel with atmospheric currents, become part of a cloud, and fall somewhere else as rain or snow. It may land directly back in the ocean, or it may fall thousands of miles away upon a mountain, forest, field, lake, or city. From there, its journey can begin again. The dissolved salt behaves differently. When ordinary ocean water evaporates, the water molecules escape into the atmosphere, while nearly all of the dissolved salts remain behind. This is the simple distinction that helps explain one of the greatest puzzles in our story. Imagine a shallow pool of seawater left behind among coastal rocks after the tide retreats. Sunlight warms the pool, and over time some of its water disappears into the air. The salt does not vanish with it. As the amount of liquid decreases, the remaining water becomes more concentrated with dissolved salts. If evaporation continues far enough, salt crystals can eventually begin forming. The same basic separation happens across the open ocean, although the sea does not simply evaporate away, because water is continually returned through precipitation, rivers, melting ice, and other parts of the global cycle. The water moves through the atmosphere and returns, while the dissolved substances follow very different pathways. Over immense periods of time, salt gradually accumulated in the oceans. This did not mean that every dissolved substance entering the sea remained there forever. As we will discover later, the ocean also has ways of removing dissolved materials, and different substances remain in seawater for different lengths of time. But the long-lasting presence of ions, such as sodium and chloride, allowed them to become extremely abundant. Rivers continually supplied dissolved material from weathered continents. Volcanic and geological processes contributed additional substances. Evaporation removed water without carrying away the dissolved salts in the same proportion. Across geological time, these processes helped create the salty oceans we recognize today. The transformation was so gradual that there was never a morning when an ancient fresh ocean suddenly became a salty one. Instead, the chemistry changed through countless interactions between water, air, rock, and the interior of the planet. And now that we understand how salt can accumulate, another question naturally appears. How salty is the ocean actually? Saying that seawater is salty tells us very little about the amount dissolved within it, and scientists need a way to compare one body of seawater with another. The answer requires us to look more closely at the chemistry hidden inside an ordinary sample of ocean water. Sodium and chloride may dominate that mixture, but they are far from alone. Magnesium, calcium, potassium, sulfate, and many other substances are present as well, each contributing to the remarkable chemical solution that fills Earth's ocean basins. By measuring those dissolved salts, we can begin to understand not only how salty the average ocean is, but why its salinity changes from one place to another, and how those differences influence the movement of the sea itself. Scientists use salinity to describe the amount of dissolved salt in seawater, giving us a way to move beyond simply saying that one body of water tastes saltier than another. Traditionally, ocean salinity has often been described in parts per thousand, which gives us an intuitive way to imagine just how much dissolved material is hidden inside water that may look perfectly clear. Average seawater contains about 35 parts per thousand dissolved salts. Put another way, if we considered 1,000 parts of typical seawater by mass, roughly 35 of those parts would consist of dissolved salts. The exact amount varies from place to place, sometimes considerably, but 35 parts per thousand provides a useful picture of average ocean water. It also reveals just how much material has become dissolved throughout the world's seas. A glass of seawater does not look as though a significant portion of what it contains once came from minerals, rocks, volcanic processes, and other parts of the Earth. Yet all of that material is present at a scale far too small for our eyes to distinguish. What we experience as a simple salty taste is the result of an extraordinary mixture of dissolved substances distributed through an ocean containing nearly 97% of all the water on our planet. Most of the dissolved salt in seawater is associated with sodium and chloride, the same two major ingredients that form sodium chloride, or common salt. Together, sodium and chloride dominate the dissolved ions in the ocean, which is why seawater tastes recognizably salty to us. Yet the chemistry is slightly different from imagining grains of table salt floating invisibly through the sea. When sodium chloride dissolves in water, it separates into sodium ions and chloride ions. Water molecules surround these charged particles and allow them to remain dispersed throughout the liquid. This is why a spoonful of salt can seem to disappear when stirred into water, even though the material itself has not vanished. If enough of the water is later removed through evaporation, sodium and chloride can once again become concentrated enough to form visible crystals. In the open ocean, however, they remain overwhelmingly dissolved, traveling with currents and mixing throughout an enormous body of water. Sodium and chloride are so abundant that they define much of what we think of as the chemistry of seawater, but they are not the only substances hidden there. Magnesium is another important component of ocean water. It occurs in much smaller quantities than sodium and chloride, yet it remains one of the major dissolved ions found in the sea. Magnesium enters the ocean through geological processes that include the weathering of rocks and interactions between seawater and Earth's crust. Once dissolved, it becomes part of the complicated chemical mixture circulating through the world's oceans. Magnesium is also important to life. Marine organisms use it in biological processes, and it participates in chemical reactions occurring within seawater and sediments. Its presence reminds us that the ocean is not simply water with table salt added to it. If we could somehow remove all of the dissolved substances from seawater and separate them according to their chemistry, we would discover a collection of materials representing many different parts of the planet. Some came from continents exposed to rain. Some were influenced by volcanic activity. Some interacted with the ocean floor. Some have passed through living organisms. The sea brings all of these pathways together. Calcium is also present in ocean water, and its story is especially interesting because marine life makes extensive use of it. Calcium can enter rivers as rocks weather on land and can eventually be transported into the ocean in dissolved form. Once there, however, it does not necessarily remain dissolved indefinitely. Many marine organisms use calcium along with carbonate to construct hard structures. Shells, skeletons, and coral reefs can therefore become part of the pathway through which dissolved material leaves seawater and enters solid biological structures. When those organisms die, some of their hard remains settle toward the ocean floor, where they can become part of sediments and over geological time contribute to the formation of rock. A calcium ion released from ancient continental rock may therefore travel through a river, enter the sea, become incorporated into the shell of a marine organism, settle onto the sea floor, and eventually become part of solid rock once again. The ocean is filled with pathways like this, which is one reason its chemistry can remain within a broad natural balance, even while rivers continually deliver new dissolved material. Potassium is another dissolved element found in seawater. Like sodium, it is present in minerals within Earth's crust and can be released through weathering. Rain and flowing water gradually interact with those minerals. Dissolved potassium can enter streams and rivers, and some of it eventually reaches the ocean. Potassium is much less abundant in seawater than sodium, but it is nevertheless an important part of ocean chemistry and an essential element for living organisms. Marine life can take it up from the surrounding environment, while geological processes can also remove or exchange potassium within the ocean system. Once again, the pattern is more complicated than materials simply entering the sea and remaining there forever. The ocean receives potassium, moves it through currents and biological systems, and exchanges it with other parts of Earth. Each dissolved substance follows its own pathways and remains in seawater for its own characteristic span of time. Sulfate adds another major component to the mixture. Sulfate is a dissolved ion containing sulfur and oxygen, and sulfur has a long history within Earth's atmosphere, rocks, volcanoes, oceans, and living organisms. Sulfur-containing compounds released through geological processes can eventually contribute to sulfate in seawater, while weathering on land also plays a role in moving sulfur compounds toward rivers and the sea. Once dissolved, sulfate becomes part of the ocean's chemical inventory and participates in both biological and geological processes. In parts of the ocean where oxygen becomes scarce, certain microorganisms can even use sulfate during their metabolism, changing it into other sulfur-containing compounds. This means that some of the chemistry of seawater is being influenced not only by rocks and volcanoes, but by microscopic life-performing chemical transformations far beyond our sight. Beyond sodium, chloride, magnesium, calcium, potassium, and sulfate, seawater contains hundreds of other dissolved substances. Some are present in extremely tiny concentrations, yet modern instruments can detect them. Elements that seem completely unrelated to the sea can exist there in trace amounts, carried by rivers, released from the crust, deposited from the atmosphere, or introduced through other natural processes. The ocean can contain minute quantities of metals and other elements dispersed through an almost incomprehensibly large volume of water. Their presence does not mean that seawater is a random mixture of everything on Earth. Different substances behave very differently once they enter the ocean. Some remain dissolved for extremely long periods. Others are rapidly used by organisms, attached to particles, incorporated into minerals, or removed through chemical reactions. The composition of seawater therefore reflects both what enters the ocean and what the ocean removes. Underwater volcanoes continue adding material to the oceans today. Far below the surface, volcanic activity occurs along parts of the seafloor where Earth's crust is being created or altered. Because these eruptions happen beneath tremendous depths of water, most people will never witness them, and many occur without any obvious sign at the surface. Yet they are part of the same planetary system that shaped the earliest oceans. Magma rises from below, volcanic material enters the marine environment, and gases and dissolved substances can become involved in the chemistry of seawater. The oceans may appear to rest calmly upon the crust, but beneath them lies a planet that is still releasing heat from its interior. In some regions, the boundary between ocean and crust becomes particularly active, and seawater can actually circulate downward through fractures before being heated and chemically transformed. This brings us to hydrothermal vents, some of the most remarkable places anywhere in the ocean. Seawater can seep through cracks in the ocean floor and travel downward into hot rock. As it is heated, the water reacts with the surrounding crust, gaining some dissolved substances while losing others. Eventually, this heated fluid can rise and emerge again through openings in the seafloor. At certain vents, the escaping fluid carries so much dissolved material that minerals begin forming as the hot fluid meets the colder seawater around it, creating dark clouds that can resemble underwater smoke. Over time, mineral deposits can build towering structures around the vents. These places reveal something fundamental about the ocean. Its chemistry is influenced not only by what washes from the continents above the surface, but by what happens deep beneath the waves, where seawater circulates through the rocky crust itself. The discovery of hydrothermal vents also transformed our understanding of the deep ocean, because these dark environments can support extraordinary communities of life. Sunlight cannot reach the deepest vent systems, so the organisms living there cannot depend directly upon the same sunlight-driven food chains familiar near the ocean surface. Instead, microorganisms can use chemical energy from substances released in vent fluids, supporting communities that may include worms, crustaceans, mollusks, and other animals. For our story, however, the vents reveal an even broader lesson. The ocean is continuously interacting with the entire planet around it. Rain connects the atmosphere to the continents. Rivers connect the continents to the sea. Evaporation connects the sea back to the atmosphere. And far below the waves, circulating seawater connects the ocean to hot rock within Earth's crust. Stretching through the world's oceans is an enormous connected system of underwater mountains known as the mid-ocean ridge system. Along these ridges, tectonic plates slowly move apart and molten material rises from deeper within Earth. As that material cools, it forms new oceanic crust, meaning that the floor beneath the sea is continually being renewed. The process is slow when measured against a human lifetime, often advancing at rates measured in only a few centimeters each year. But geological time transforms those tiny movements into changes that can reshape entire ocean basins. New rock forms along the ridges and gradually moves away as still newer crust appears behind it. Seawater circulates through fractures in this young crust. Heat from below drives chemical reactions, and hydrothermal systems exchange substances between the ocean and the solid earth. The seafloor beneath seemingly peaceful water is therefore part of a restless planetary surface that has never stopped changing. Even today, while waves move gently across the ocean above, new pieces of the ocean floor are quietly being created far below. This continuous creation of crust is part of the larger process known as plate tectonics, and plate tectonics constantly reshapes Earth's ocean basins. The outer portion of our planet is divided into large moving plates that carry both continents and oceanic crust. These plates move so slowly that their motion is impossible to notice simply by standing on the ground, yet over millions of years they can rearrange the geography of the planet. Continents that are now separated by thousands of miles were once joined. Oceans have opened between drifting land masses, widened for millions of years, and in other places gradually disappeared as oceanic crust descended back into Earth's interior. The Atlantic Ocean, for example, has not existed in its present form throughout Earth's entire history. Its basin developed as land masses separated and new oceanic crust formed between them. Other ancient oceans once occupied parts of the planet where continents now stand. The map of Earth that seems so permanent to us is therefore only one moment in an extraordinarily long sequence of changing arrangements. This movement helps explain something surprising about the rocks beneath the sea. Although Earth's oceans are ancient, most of the ocean floor itself is much younger than the oldest continental rocks. New oceanic crust is created along spreading ridges, moves slowly away from those ridges, and can eventually reach regions where one tectonic plate descends beneath another. There, old oceanic crust can sink into Earth's mantle and become recycled. Continental crust behaves differently and can preserve ancient rocks for much longer periods. Some continental minerals have survived from more than 4 billion years ago, while the present ocean floor is dramatically younger. This means that an ocean basin can contain water whose history stretches far into the ancient past, while resting upon crust that has been created, moved, and replaced much more recently. The floor of the sea is not an untouched record, extending all the way back to the first oceans. Much of that earliest oceanic crust has long since disappeared into Earth's interior. The constant renewal of the seafloor matters to the chemistry of seawater because newly created oceanic crust provides fresh material with which seawater can interact. Water enters fractures, encounters minerals in the rock, becomes heated in some regions, and participates in chemical reactions that can either add substances to seawater or remove them from it. The ocean and crust are therefore exchanging material rather than behaving as completely separate systems. This helps us return to the mystery we raised near the beginning of our journey. If rivers and geological processes continually deliver dissolved substances to the ocean, why has the sea not simply become more and more concentrated with every passing age? The answer is that substances do not only enter the ocean, they also leave it, and some of the pathways by which they leave are just as important as the pathways that brought them there. Different dissolved minerals behave in very different ways once they enter seawater. Some remain dissolved for extremely long periods, which allows them to become abundant throughout the world's oceans. Others are removed much more quickly. A dissolved substance may react chemically with another material, become attached to a particle, be incorporated into a newly forming mineral, or be taken up by a living organism. Eventually, some of this material settles toward the seafloor. The ocean is therefore not a container into which every arriving mineral is permanently deposited. It is more like an enormous moving reservoir through which materials continually pass. Some remain for a very long time. Others travel through the system comparatively quickly. The amount of any particular substance in seawater depends partly upon the balance between how quickly it enters and how quickly natural processes remove it. Marine organisms provide one important pathway for that removal. Throughout the oceans, living things take dissolved substances directly from the water and use them to build their bodies. Some organisms use calcium and carbonate to construct hard shells or skeletons. Tiny plankton floating near the surface can produce intricate mineral structures that may be smaller than a grain of sand. Mollusks build shells, and many other marine creatures create hard parts from substances obtained from their surroundings. While the organism is alive, material that was once dissolved freely in seawater has become incorporated into a solid biological structure. When the organism dies, that structure may dissolve again, be eaten by another organism, or begin sinking toward the bottom. Some eventually reaches the seafloor and becomes part of the accumulating sediment. In this way, life participates directly in the movement of chemical substances out of seawater and into solid material. Coral reefs provide a particularly striking example of this process. Corals are animals, and reef-building corals produce hard skeletons made largely from calcium carbonate. Generation after generation can add new material to the structures left by earlier corals, eventually creating reefs large enough to be seen from space. These enormous formations begin with substances that were once dissolved in seawater. Calcium and carbonate become incorporated into solid skeletons, temporarily removing those ingredients from the surrounding water. Coral reefs are not simply beautiful habitats filled with colorful marine life. They are also part of the chemical relationship between the ocean, living organisms, and solid mineral material. Over geological time, carbonate material produced by marine organisms can accumulate in tremendous quantities, become buried, and eventually contribute to limestone and other sedimentary rocks. Other dissolved materials become trapped within ocean sediments. The seafloor receives a slow but persistent rain of particles from the water above. Some are fragments of rock delivered from continents. Some are dust carried through the atmosphere. Others are the remains of microscopic organisms that once lived near the surface. Chemical reactions can also create new particles directly within seawater. Layer after layer accumulates across the bottom, although the rate can be extraordinarily slow in the deepest and most remote regions of the ocean. As sediments build, substances can become incorporated into them and gradually removed from active circulation in seawater. Burial can eventually carry this material deeper beneath the seafloor, where increasing pressure, temperature, and chemical changes may transform it further. A dissolved element that once traveled freely with an ocean current can therefore end its journey, locked within sediment, for millions of years. Chemical reactions beneath the seafloor remove additional minerals from seawater. Water circulating through oceanic crust does not simply become heated and return unchanged. It reacts with the minerals surrounding it. Some dissolved substances are added to the water, while others are taken from it and incorporated into altered rock. At hydrothermal systems, this exchange can be especially intense. Seawater enters cracks in the crust, travels through hot regions, reacts chemically with the rock, and eventually emerges with a composition very different from the water that originally descended. Magnesium, for example, can be removed from seawater during reactions within hot oceanic crust, while other elements can be added to the circulating fluid. When the heated water returns to the ocean and cools, additional minerals may precipitate from it. The same hydrothermal systems that contribute certain substances to seawater can therefore help remove others. Together, these processes reveal that salt enters and leaves the oceans in a long-term natural balance. Rivers carry dissolved material from weathered continents. Volcanoes and interactions with the crust contribute additional substances. At the same time, marine organisms incorporate minerals into shells and skeletons. Particles settle into sediments. Chemical reactions alter the oceanic crust, and tectonic processes eventually carry some material back into Earth's interior. The balance is not perfectly motionless, nor has ocean chemistry remained identical throughout all of Earth's history. Conditions have changed as continents moved, climates shifted, life evolved, and geological activity varied. But the modern ocean exists within a vast system of inputs and outputs that prevents every dissolved substance from simply accumulating without limit. This is the answer to the second mystery we raised at the beginning. The ocean can remain salty for immense periods without becoming endlessly saltier, because the story is not simply about what enters the sea, it is also about what leaves. Not every ocean has the same salinity, even though the world's major oceans are connected and their waters are continually mixed by currents. The differences are created largely by the balance between water entering and leaving a particular region. Salt remains dissolved in the sea, while the amount of water surrounding it can change, so adding fresh water tends to lower salinity, while removing water tends to raise it. This means that climate has an important influence on how salty seawater becomes. A region that receives abundant rainfall may have lower surface salinity than another region where the air is dry and evaporation is intense. The difference does not require one ocean to contain a completely different kind of salt from another. Instead, much of the variation comes from changing the concentration of the salts already dissolved within the water. Just as a small amount of water added to a salty solution makes it less concentrated, while removing some of the water makes the remaining solution more concentrated, the enormous oceans respond to changes in their supply and loss of fresh water. High evaporation usually increases salinity because evaporation removes water while leaving nearly all of the dissolved salt behind. This effect is especially important in warm regions, where dry conditions and abundant sunlight allow large quantities of water to enter the atmosphere. As water molecules escape from the ocean surface, the amount of salt in the remaining water becomes more concentrated. The change from one day to the next may be small, but persistent evaporation across a large area can create measurable differences in salinity. Some enclosed or partly enclosed seas can become particularly salty when evaporation is strong and the exchange of water with the open ocean is limited. In these places, water may leave rapidly through evaporation, while dissolved salts remain within the basin. The same basic principle operates in the open ocean, although currents continually move water around and prevent most regions from behaving like isolated containers. Heavy rainfall usually has the opposite effect. When large amounts of fresh rain fall directly onto the ocean, they add water without adding a comparable amount of salt. Surface seawater becomes diluted, and its salinity decreases. Tropical regions can receive tremendous quantities of rainfall, particularly where warm, moist air rises and produces frequent storms. Although high temperatures in the tropics can also encourage evaporation, the balance between rainfall and evaporation determines which influence becomes stronger in a particular location. A region receiving more fresh water than it loses can develop lower surface salinity, while another region experiencing stronger evaporation can become saltier. This is one reason latitude alone cannot tell us exactly how salty a particular part of the ocean will be. Salinity reflects the combined influence of rainfall, evaporation, currents, rivers, freezing, melting, and the movement of water from one region to another. Large rivers can temporarily reduce the salinity of nearby seawater for the same reason. When an enormous river reaches the coast, it delivers a tremendous volume of fresh water into the marine environment. Near the river mouth, this fresh water mixes with seawater and lowers its salinity. The effect can extend well beyond the immediate coastline when the river carries enough water and ocean currents transport the fresher surface water outward. The boundary between river water and ocean water is not always a sharp line. Instead, there can be broad regions where the two gradually mix, creating water with a salinity between that of a river and the open sea. These environments are common around estuaries and large river deltas, where changing tides, river flow, storms, and seasons continually alter the mixture. During periods of heavy rain, a river may deliver more fresh water and lower coastal salinity further. During drier periods, the influence may weaken, and saltier ocean water may extend closer to the river mouth. Polar oceans are generally less salty than many warmer ocean regions because the balance of fresh water is different near the frozen parts of the planet. Melting snow and ice can add fresh water to the ocean, while cold temperatures greatly reduce evaporation compared with warm, subtropical regions. Large rivers also deliver fresh water into parts of the Arctic Ocean, contributing to relatively low salinity near the surface. The pattern is not identical everywhere, because currents can carry saltier water toward the poles, and local conditions vary, but the general relationship between climate and salinity remains clear. Where fresh water is added and relatively little water is lost through evaporation, seawater tends to become less salty. Where evaporation removes large amounts of water and fresh water input is smaller, salinity tends to rise. In this way, the distribution of salt across the oceans reflects the movement of water through Earth's climate system. Sea ice introduces another important part of this pattern. Although sea ice forms from seawater, the ice itself contains very little salt compared with the liquid water from which it formed. As seawater begins freezing, water molecules arrange themselves into the crystal structure of ice. Most of the dissolved salts do not fit easily into that structure, so they are largely excluded from the growing ice. Some salty liquid can become trapped within small channels and pockets, especially when the ice is young, but much of the salt remains in the liquid ocean below and around it. This means that sea ice should not be imagined as simply frozen seawater with exactly the same salt concentration it had before freezing. The freezing process separates much of the water from its dissolved salts. As sea ice continues forming, most of the rejected salt is left behind in the surrounding seawater. This can make the nearby liquid water saltier. The effect is particularly important because increasing salinity also increases the density of seawater. Cold water is already relatively dense, and when freezing leaves additional salt behind, the remaining water can become denser still. In some polar regions, this dense water can sink beneath lighter water and begin moving through the deep ocean. A process occurring at the surface of a frozen sea can therefore contribute to the movement of water far below. The salt itself has not disappeared. It has been redistributed, concentrated in the liquid water, while much fresher ice remains above it. When sea ice melts, the process moves in the opposite direction. The ice releases water containing relatively little salt back into the ocean, slightly lowering the salinity of the surrounding seawater. During seasons when large areas of sea ice melt, this fresh water can create a less salty surface layer. When freezing returns, salt is once again rejected from the forming ice, and the remaining water becomes saltier. This seasonal exchange is another example of how ocean salinity can change, even though the total quantity of salt in the entire ocean does not need to change very much. Salt can be moved, concentrated, diluted, temporarily stored, and released as water changes between liquid and solid forms. Ocean currents then move salt throughout the world's oceans. Water does not remain in the region where rain fell upon it, where a river entered the sea, or where ice froze around it. Surface currents can carry water across entire ocean basins, while deeper currents move enormous volumes through the dark regions below. As water travels, it carries its dissolved salts with it. A parcel of relatively salty water formed in a region of strong evaporation can be transported elsewhere and mixed with less salty water. Fresh water added near a river mouth can spread along a coastline or outward into the sea. Polar water influenced by freezing and melting can move into other regions. Currents continually blur the boundaries between these different water masses, while also preserving broad patterns that scientists can measure. Salinity helps determine the density of seawater, which gives these differences an importance far beyond their chemical composition. Water containing more dissolved salt is generally denser than otherwise similar water containing less salt. Temperature matters as well, because colder seawater is generally denser than warmer seawater. Together, temperature and salinity help determine whether a body of seawater tends to remain near the surface, mix with surrounding water, or sink into deeper parts of the ocean. A change in salinity that might seem insignificant when expressed as a small difference in concentration can therefore influence the movement of an enormous mass of water. When seawater becomes sufficiently dense, it can sink beneath less dense water. This is particularly important in certain high-latitude regions where surface water becomes very cold and, in some places, saltier as sea ice forms. Dense water can descend into the deep ocean and then begin spreading away from the region where it sank. The movement is slow compared with the waves and currents we can easily see at the surface, but the quantity of water involved is enormous. This sinking connects the surface ocean with the deep sea and helps drive patterns of circulation extending through multiple ocean basins. Deep ocean currents connect every major ocean basin as part of a vast global circulation system. Water that sinks in one region can travel through the deep ocean for extraordinarily long periods before eventually returning toward the surface elsewhere. These currents link distant parts of the Atlantic, Pacific, Indian, Southern, and Arctic oceans, moving water, dissolved gases, nutrients, heat, and salt around the planet. The circulation is influenced by differences in temperature and salinity, as well as by winds, the rotation of Earth, the shapes of ocean basins, and interactions with the seafloor. What began in our story as a question about dissolved salt has therefore led us into one of the great moving systems of the planet. The salt carried into the oceans over billions of years does not simply remain where it first arrived. It travels with the water, helps influence its density, and participates in a global circulation that connects the seas of the world. This global circulation helps regulate Earth's climate by moving enormous quantities of water between different parts of the ocean. The process is slow compared with the movement of waves across a beach, yet its influence reaches across the planet. Water that becomes cold and dense in certain regions can sink and enter the deep ocean, while water elsewhere eventually rises toward the surface again. Salinity contributes to these differences in density, linking the dissolved salts in seawater to the movement of some of the largest currents on Earth. The circulation does not operate like one simple river flowing along a single path beneath the sea. Instead, it is a complicated network influenced by temperature, salinity, winds, the rotation of Earth, the shapes of continents, and the contours of the ocean floor. Over long periods, this movement allows distant ocean basins to exchange water and helps redistribute heat, dissolved gases, nutrients, and salt. A change occurring in one part of the ocean can therefore become connected to conditions thousands of miles away, reminding us that the seas surrounding separate continents are parts of one enormous planetary system. The oceans are able to influence climate so strongly in part because they store enormous amounts of heat from the sun. Water can absorb a great deal of energy while changing temperature more slowly than land, allowing the oceans to act as a vast reservoir of heat. During daylight, sunlight reaches the ocean surface, and some of its energy is absorbed by the water. Winds and waves help mix this warmth downward, while currents move heated water away from the places where the energy originally entered the sea. The amount of solar energy received is not the same everywhere. Regions closer to the equator generally receive more direct sunlight over the course of the year than regions closer to the poles. If the ocean simply remained still, these differences would create an even greater contrast between warm and cold parts of the planet. But seawater is continually moving, and that movement allows some of the heat stored in warmer regions to be transported elsewhere. Ocean currents carry heat around the planet, sometimes across entire ocean basins. Warm surface currents can move water away from tropical and subtropical regions toward higher latitudes, while colder currents can carry cooler water toward warmer regions. The atmosphere also exchanges heat with the ocean above these currents, which means that the temperature of seawater can influence the air passing over it. In some places, warm currents help moderate nearby climates, while cold currents can help keep coastal regions cooler than their latitude alone might suggest. The movement of heat through the ocean is not controlled by salinity alone. Winds are extremely important in driving surface currents, and Earth's rotation helps shape their paths. Yet the deeper circulation we have just explored is influenced partly by differences in density created by temperature and salinity. Salt therefore remains connected to the larger system, not because it single-handedly controls climate, but because it helps determine how seawater behaves as part of the moving ocean. The oceans also influence weather patterns across the globe. Water continually exchanges heat and moisture with the atmosphere, and changes in ocean temperature can affect the air above. Warm ocean surfaces provide energy and water vapor to the atmosphere, while cooler waters can alter the stability and temperature of nearby air. Winds, storms, rainfall patterns, and large atmospheric circulation systems are all connected in different ways to conditions at the ocean surface. Coastal regions, often experience the moderating influence of nearby water because the ocean warms and cools more slowly than land. Farther away, changes in ocean temperatures can influence weather patterns across entire continents. The ocean and atmosphere are not separate systems operating independently. They are constantly exchanging energy and water, and the behavior of one can alter the behavior of the other. One of the clearest examples of this connection occurs across the tropical Pacific Ocean during El Niño. Under more typical conditions, winds help push warm surface water toward the western Pacific, while colder water rises closer to the surface in parts of the eastern Pacific. During an El Niño event, this familiar pattern changes. Surface waters across parts of the central and eastern tropical Pacific become unusually warm, and the winds and atmospheric circulation associated with the region also shift. Those changes can influence rainfall and temperature patterns far beyond the Pacific itself. Some areas may experience increased rainfall, while others become unusually dry, and the effects can extend into regions thousands of miles from the warm ocean water where the event is measured. El Niño does not occur because the ocean is salty, but it demonstrates how changes in ocean conditions can become connected to weather across the globe. La Niña creates a different pattern of ocean temperatures across the tropical Pacific. During La Niña conditions, parts of the central and eastern tropical Pacific become cooler than usual, while the normal pattern of winds and ocean circulation becomes stronger in important ways. The distribution of warm water shifts, and the atmosphere responds. As with El Niño, the effects can extend far beyond the tropical Pacific, influencing rainfall, temperatures, and storm patterns in different parts of the world. El Niño and La Niña are opposite phases of a larger interaction between the tropical ocean and atmosphere, and neither produces exactly the same weather everywhere each time it occurs. Their importance to our story is that they reveal how deeply the ocean is connected to the environment above it. The sea does not merely occupy the low spaces between continents. Its temperature, movement, and chemistry form part of a planetary system that influences conditions experienced far inland. Stable ocean chemistry also helps create the conditions in which marine life can thrive. The word stable does not mean that seawater never changes. We have already seen that salinity varies with evaporation, rainfall, rivers, freezing, melting, and currents. Ocean chemistry has also changed over the immense history of Earth, but marine organisms live within particular ranges of temperature, salinity, acidity, oxygen, nutrients, and other chemical conditions, and many have evolved remarkable ways of functioning within the environment of seawater. Some organisms tolerate broad changes in salinity, while others survive only within a much narrower range. The chemistry surrounding an organism influences the movement of water and dissolved substances through its cells, the minerals available for building hard structures, and countless chemical reactions required for life. The ocean is therefore not simply a place where organisms happen to live. The properties of seawater form part of the environment to which marine life has adapted over billions of years. Among the smallest organisms in the sunlit ocean are phytoplankton, microscopic organisms that drift with currents near the surface and form the foundation of most marine food webs. They are easy to overlook because many are far too small to see individually without magnification, yet collectively they support an extraordinary amount of life. Phytoplankton use sunlight and nutrients to produce organic matter through photosynthesis. Tiny animals known as zooplankton feed on them, and those animals can then become food for fish and other creatures. Energy passes through increasingly complex food webs, ultimately supporting animals ranging from small schooling fish to some of the largest creatures in the sea. A vast marine ecosystem can therefore depend upon organisms so small that an individual one may be invisible to a person looking into the water. Phytoplankton also produce a significant portion of Earth's oxygen through photosynthesis. Like plants on land, photosynthetic phytoplankton use light energy to transform carbon dioxide and water into organic material, releasing oxygen as part of the process. Across the enormous sunlit surface of the world's oceans, the combined activity of these microscopic organisms makes a major contribution to global oxygen production. Not every oxygen molecule they produce remains available in the atmosphere indefinitely, because oxygen is also consumed through respiration and decomposition, but their overall role in Earth's oxygen cycle is immense. The connection is particularly striking when we remember the early Earth described at the beginning of our journey, when the atmosphere contained almost no free oxygen. Over geological time, photosynthetic life helped transform the chemistry of the planet, and today some of that activity continues within the same oceans whose earliest waters formed billions of years ago. Coral reefs support some of the most diverse ecosystems in the ocean. Reef-building corals create hard calcium carbonate skeletons, and over many generations these structures can grow into enormous formations filled with cracks, surfaces, caves, and sheltered spaces. Fish, crustaceans, mollusks, worms, microorganisms, and countless other creatures can use these habitats for food, shelter, reproduction, and protection. Although coral reefs occupy only a small portion of the ocean, their biological richness can be extraordinary. Their existence also connects back to the chemical balance we explored earlier. Corals require suitable seawater conditions to build and maintain their skeletons, and the minerals incorporated into a reef were once dissolved in the surrounding sea. A reef is therefore both an ecosystem and a visible record of the exchange between marine organisms and ocean chemistry. Countless marine species depend upon the chemical balance of seawater. Some animals maintain internal salt concentrations different from the water surrounding them, and must continually regulate the movement of water and ions through their bodies. Others are especially sensitive to changes in salinity and survive only within particular environments. Creatures living near river mouths may experience changing mixtures of fresh and salt water with every tide, while animals of the open ocean inhabit conditions that are generally more stable. From microscopic plankton to fish, corals, mollusks, and the enormous animals that travel between ocean basins, life in the sea has evolved within the chemical environment created by billions of years of interaction between water and earth. Yet some of the most productive places influenced by this relationship are found along the boundary between land and sea, where salt water and fresh water meet, and where specialized ecosystems have developed among marshes, mangrove forests, and underwater meadows. Along the edges of continents, where land and ocean meet, salt marshes provide habitat for many coastal animals. These wetlands commonly develop in sheltered coastal areas, where tides regularly move seawater across low-lying ground, creating an environment that is neither completely terrestrial nor permanently submerged beneath the sea. The plants growing there must tolerate salty conditions that would be difficult for many ordinary land plants, and their stems and roots create shelter for a remarkable variety of living things. Fish can move into flooded areas with the tides, while crabs, snails, Insects, birds, and other animals feed and reproduce within the marsh. Young fish can find protection among dense vegetation before moving into deeper coastal waters, and migrating birds may depend upon these wetlands as places to rest and feed during long journeys. The tides continually bring water into the marsh and carry it away again, moving nutrients and organic material between the wetland and nearby coastal waters. Salt marshes therefore occupy a constantly changing boundary, shaped by the same salty ocean, whose origins we have been following from the earliest history of Earth. Mangrove forests provide another remarkable coastal habitat, particularly along warm tropical and subtropical shorelines. Mangrove trees are adapted to conditions that would overwhelm many other trees, growing where their roots may be surrounded by salty or partly salty water, and where changing tides repeatedly flood the ground. Their complicated networks of roots slow moving water and help hold sediment in place, reducing erosion along parts of the coastline. Waves moving toward shore lose some of their energy as they pass through dense roots and vegetation, while suspended particles can settle from the water and become trapped among them. This ability to stabilize coastal sediments means that mangrove forests can provide a natural measure of protection for shorelines, while also creating valuable habitat. Small fish, crustaceans, mollusks, birds, and many other organisms use these forests, and submerged roots can serve as sheltered nursery areas for young marine animals. Once again, the meeting of salt water and land creates an environment that depends upon the particular chemistry and movement of the sea. Beneath shallow coastal waters, seagrass meadows form another important ecosystem. Seagrasses are flowering plants adapted to life beneath the water, and they can grow in broad underwater fields, where enough sunlight reaches the seafloor. Their leaves provide food and shelter for marine animals, while their roots and underground stems help stabilize sediments. Seagrass meadows also capture carbon through photosynthesis, and some of that carbon can eventually become stored within the sediments beneath them. When organic material becomes buried in low oxygen sediment, part of its carbon can remain stored for long periods, rather than quickly returning to the atmosphere. In this way, an underwater meadow can participate in the movement of carbon through the Earth system, while also supporting marine life. Salt marshes, mangroves, and seagrass meadows are very different environments, but all three demonstrate how the boundary between land and salty water can create productive habitats shaped by tides, sediments, chemistry, and the continual movement of the sea. Only a small percentage of Earth's water is fresh, and much of that fresh water is not immediately available in rivers and lakes. Large quantities are stored in glaciers and ice sheets, while another significant portion exists underground. The fresh water visible in streams, rivers, and lakes is therefore only a small fraction of Earth's total water supply. This creates an interesting contrast with the journey we have been following. Rain falls fresh, rivers generally flow fresh, and the water vapor that rises from the ocean through evaporation is essentially fresh, yet the great reservoir into which so much of that water eventually returns is salty. The water cycle continually moves water between these different reservoirs, while dissolved salts follow their own pathways. This separation between moving water and the substances dissolved within it has helped preserve the great difference between the fresh water of the continents and the salty water of the oceans. Long before people understood the chemistry responsible for ocean salinity, they learned that salt itself was extraordinarily useful. Humans have harvested sea salt for thousands of years, taking advantage of the same principle of evaporation that helps explain why salt remains behind when ocean water enters the atmosphere. In warm and dry regions, seawater could be directed into shallow pools or ponds where sunlight and moving air gradually removed the water. As evaporation continued, the dissolved salts became increasingly concentrated until crystals could form and be collected. Other communities obtained salt from natural deposits on land or from salty springs, but coastlines offered access to an almost unimaginably large reservoir. The people gathering salt did not need to understand sodium ions, chloride ions, chemical weathering, or hydrothermal vents to recognize that seawater could leave something valuable behind when the water disappeared. Salt became especially important because ancient civilizations depended upon it to preserve food. Before mechanical refrigeration existed, keeping meat, fish, and other foods from spoiling for long periods was a serious challenge. Salt offered one solution. When used in sufficient amounts, it draws water from food and creates conditions that make it more difficult for many microorganisms responsible for spoilage to grow. Salting could therefore extend the useful life of food and make it easier to store supplies for seasons when fresh food was scarce. Fish caught in abundance could be preserved rather than eaten immediately, while meat could be treated so that it lasted much longer than it otherwise would. The ability to preserve food had practical importance for households, travelers, sailors, armies, and communities preparing for periods when harvesting or hunting became difficult. Something that began in our story as dissolved ions released from rocks eventually became a substance woven deeply into everyday human survival. Because salt was necessary and not equally easy to obtain everywhere, it became one of history's valuable trade goods. Communities with reliable access to salt could exchange it with people living in regions where the mineral was harder to acquire. Salt from coastal evaporation ponds, inland deposits, mines, and salty springs entered networks of exchange that connected settlements and regions. Its value did not come from rarity alone, because enormous quantities existed in nature. What mattered was access, production, transportation, and need. Salt was useful to almost everyone, particularly in societies that depended upon food preservation, yet obtaining clean and dependable supplies could require considerable labor. Mining salt from underground deposits could be difficult, while producing it from seawater depended upon suitable conditions and the ability to move the finished product inland. Some ancient trade routes developed in part to transport salt from places where it could be produced or mined to communities where it was needed. Caravans carried salt across difficult landscapes, merchants moved it along roads and rivers, and coastal trade allowed supplies to travel between ports. In some regions, blocks or loads of salt could travel enormous distances from their source before reaching the people who ultimately used them. These routes rarely carried only one product forever, because successful trading networks could move many different goods. But salt was important enough to help sustain commerce across regions where access to it varied greatly. A substance dissolved invisibly throughout the oceans could therefore influence where people traveled, which communities interacted, and how goods moved across the ancient world. Entire cities and regions could grow wealthy through access to salt production and trade. Places near productive salt works, mines, or important transportation routes could benefit from controlling or taxing the movement of a commodity that people continually needed. Governments also recognized its value, and in different periods of history, salt production or trade could become subject to taxes, regulation, or state control. The importance of salt was not identical in every civilization, but its usefulness gave it a place in economies across widely separated parts of the world. What makes this particularly remarkable is how far our story has traveled without ever truly leaving the same substance. We began with rain falling upon ancient rock, followed dissolved minerals into rivers, watched water evaporate while salt remained behind, and then saw that same basic property become useful to people who learned to harvest crystals from salty water. As people became increasingly skilled at traveling across the sea, sailors learned to navigate salty oceans long before the invention of modern instruments. Early mariners could not depend upon satellite navigation, electronic charts, or precise clocks, yet they found ways to cross stretches of water that might appear almost featureless to an inexperienced observer. They watched the position of the sun and stars, recognized familiar coastlines, studied the direction of winds, and learned how currents influenced the movement of their vessels. Experienced sailors could also notice patterns in waves, clouds, birds, and changing water conditions that offered clues about nearby land or approaching weather. Knowledge was often accumulated across generations, allowing communities to travel between islands, along coastlines, and eventually across great distances. The ocean could be dangerous and unpredictable, but it also became a pathway connecting societies that might otherwise have remained separated by enormous expanses of water. The same currents that distribute salt and heat around the planet could help or hinder a voyage, and understanding their behavior became increasingly valuable as human exploration expanded. The salinity of seawater also affects ships in a simple but important way, because salt water is denser than fresh water. A floating vessel is supported by the upward force created as it displaces water, and denser water provides slightly greater buoyancy. As a result, a ship generally floats a little higher in salt water than it does in fresh water. The difference may seem small, but for heavily loaded vessels, it can matter. A ship moving from the open sea into a freshwater river or harbour can settle slightly deeper into the water, even though nothing has been added to its cargo. Sailors and ship operators eventually came to account carefully for differences in water density when determining how deeply a vessel could safely be loaded. Here again, the dissolved minerals in seawater produce an effect that reaches beyond taste or chemistry. The salt changes a physical property of the water itself, and that change can influence something as large as a ship carrying people and cargo across the world. Some bodies of water demonstrate this effect far more dramatically than the ordinary ocean. The Dead Sea is famous for its extremely high salinity, which makes its water much denser than typical seawater. Despite its familiar name, the Dead Sea is actually a landlocked salt lake, rather than part of the world's connected ocean. Water flows into it, but there is no river carrying its water onward to another sea. In the region's dry climate, intense evaporation removes water from the lake, while dissolved salts remain behind. Over time, this has produced concentrations far greater than those found in the open ocean. A person entering the Dead Sea experiences unusually strong buoyancy and can float with remarkable ease because the dense water provides greater upward support. The effect offers an exaggerated demonstration of the same principle operating everywhere in seawater. The more dissolved salt water contains, the greater its density generally becomes, provided other conditions such as temperature are taken into account. The Dead Sea is only one example of an inland salt lake shaped by evaporation. Salt lakes form in places where water enters a basin but has little or no route to flow outward toward the ocean. Rivers and streams bring dissolved minerals into the lake, just as rivers carry dissolved material toward the sea. If the only major way for water to leave is through evaporation, the water escapes into the atmosphere while most of its dissolved salts remain behind. Continued evaporation can gradually concentrate those salts, sometimes creating water far saltier than the ocean. The exact chemistry differs among lakes because the surrounding rocks, incoming rivers, climate, and geological history are different. But the basic process is familiar from the story we have already followed. Water enters carrying dissolved material. Water later leaves as vapor. Much of the dissolved material stays behind. In a closed basin, this concentration can become especially dramatic because there is no outlet carrying the accumulated salts away. Some ancient seas experienced this process on an enormous scale and eventually left behind vast underground salt deposits. During certain periods of Earth's history, bodies of seawater became partly or almost completely isolated from the open ocean. If evaporation removed water faster than new seawater replaced it, the concentration of dissolved salts increased. As the water became increasingly concentrated, minerals began to crystallize and settle onto the bottom. Continued evaporation could produce thick layers of salt and other minerals. Later, those deposits might be buried beneath younger sediments and preserved underground for millions of years. Many of the salt deposits mined on land today are therefore remnants of ancient bodies of salty water. A miner working far from the modern coastline can be extracting material that formed when seawater once occupied a landscape that has since been transformed by geological change. These ancient deposits reveal another route by which salt can leave the ocean. When seawater evaporates in a restricted basin and solid salt minerals form, dissolved ions that once moved freely through the water become locked into solid deposits. If those deposits are buried and preserved, their salts can remain outside the ocean for extraordinary lengths of time. This process has occurred repeatedly during Earth's history as seas opened, closed, became isolated, and changed with the movement of continents and variations in sea level. The resulting layers can become hundreds or even thousands of feet thick in some geological settings. Over time, pressure from overlying sediments can cause buried salt to behave in unusual ways, slowly deforming and moving through surrounding rock. What began as dissolved material in seawater can therefore become part of the solid geology of a continent. The connection between ancient oceans and modern land becomes especially clear when salt deposits are mined. Rock salt is largely composed of the mineral halite, which is the crystalline form of sodium chloride. It can occur underground in extensive beds created by the evaporation of ancient salty water. Mining these deposits allows people to obtain salt without using modern seawater at all, although the material ultimately owes its existence to an ancient water body and the same process of evaporation we have already encountered. Some deposits formed so long ago that the geography of Earth was dramatically different when their salt crystallized. Continents occupied different positions, climates were different, and seas existed in places that are now dry land. A piece of rock salt taken from underground can therefore be thought of as a small remnant of vanished water, preserved long after the sea that created it disappeared. Modern salt production still uses both mining and evaporation. In suitable coastal climates, seawater can be moved into shallow ponds, where sunlight and dry air gradually remove the water. As the ponds become more concentrated, different minerals can begin crystallizing, and eventually sodium chloride can be collected. The principle is remarkably simple and would have been recognizable to people living thousands of years ago, even though modern production can operate on a much larger scale. Elsewhere, salt is mined from underground deposits using conventional mining methods or by dissolving buried salt with water and bringing the resulting brine to the surface. The source may be a modern ocean or an ancient deposit, but in both cases, the salt ultimately reflects the ability of water to carry dissolved ions and the ability of evaporation to separate that water from the substances dissolved within it. Salt also plays an important role in modern industry. Sodium chloride is used not only for food and seasoning, but as a raw material for producing chemicals required in manufacturing. Industries use salt in processes connected with products ranging from glass and paper to textiles, soaps, detergents, and many other materials. Large quantities are also used to soften water and for other industrial purposes. The familiar crystals kept in a kitchen therefore represent only a small part of humanity's use of salt. The substance that once traveled invisibly through ancient rivers and accumulated within oceans has become an important industrial resource, extracted and processed on enormous scales. Its usefulness continues to connect human activity with the geological and chemical processes that created natural salt deposits long before civilization existed. In colder climates, salt is also spread on roads because dissolved salt lowers the freezing point of water. Pure water freezes at a particular temperature under ordinary conditions, but when salt dissolves into the thin layer of liquid water present on ice, it makes freezing more difficult. This can help melt ice when temperatures are within an effective range and can reduce the formation of dangerous frozen surfaces on roads. The process is another consequence of the way dissolved ions change the physical properties of water. Salt affects density, freezing, and other characteristics of a solution, which is why the chemistry we have been exploring has practical effects far beyond the ocean. The same principle helps us understand why ordinary seawater generally freezes at a lower temperature than fresh water, and why forming sea ice rejects much of its dissolved salt into the surrounding ocean. Yet for all the salt humans mine, harvest, trade, and use, the quantity dissolved in the world's oceans remains almost beyond comprehension. The seas contain an enormous reservoir accumulated and regulated through geological processes operating across billions of years. Human beings have learned to extract tiny portions of it and make use of the properties that arise when salt interacts with water. But understanding the ocean itself requires much more precise measurements. Scientists need to know how salinity differs from one place to another, how it changes with depth and season, and how those changes relate to currents, rainfall, evaporation, rivers, and ice. Measuring the saltiness of seawater has therefore become an important part of modern oceanography, and the methods used to do it reveal something else about salt water that is invisible to our eyes, but easy for scientific instruments to detect. The dissolved ions in seawater change the way electricity moves through it, providing researchers with a precise way to measure the hidden salt carried within the sea. Because dissolved salts separate into electrically charged ions when they enter water, seawater conducts electricity far better than pure fresh water. Sodium ions carry a positive electrical charge, while chloride ions carry a negative charge, and the many other dissolved ions in seawater also contribute to its ability to conduct an electrical current. This property gives oceanographers a useful way to study salinity without having to remove the water and weigh every bit of salt dissolved within it. Instruments can measure the electrical conductivity of a seawater sample, and that measurement can be used together with temperature and pressure to determine its salinity with great precision. Modern oceanographic instruments can make these measurements repeatedly as they travel through different depths of the sea, allowing scientists to build detailed profiles of how ocean conditions change from the warm surface waters to the cold darkness far below. What seems to us like a simple glass of salty water therefore contains electrical properties that can reveal exactly how much dissolved material is present and help researchers identify different bodies of seawater as they move through the ocean. Satellites can also help scientists estimate salinity at the ocean surface, allowing researchers to observe patterns across areas far too large to measure continuously from ships alone. They do not taste the ocean or collect bottles of water from hundreds of miles above Earth. Instead, specialized instruments detect tiny changes in microwave energy naturally emitted from the ocean surface, which are influenced by salinity, along with factors such as temperature and surface conditions. From these measurements, scientists can create maps showing broad patterns of surface salinity across the world's oceans. Regions where evaporation is strong often stand out from regions receiving abundant rainfall or large quantities of river water. Repeated observations allow researchers to watch these patterns change through seasons and from one year to another. Satellite measurements therefore give us a view of ocean saltiness that would have been impossible for earlier generations, revealing the movement of fresh and salty water across enormous portions of the planet at once. Scientists also collect direct measurements from research ships, where instruments can be lowered from the surface into the deep ocean. One of the most important tools used in oceanography measures conductivity, temperature, and depth, allowing researchers to examine several properties of seawater together. As the instrument descends, it records changes that may occur hundreds or thousands of feet below the surface. Water that appears uniform from above can contain distinct layers with different temperatures and salinities. Samples can also be collected at selected depths and brought aboard the ship for further analysis. These measurements help scientists determine how different water masses are distributed and how they change over time. A research vessel may occupy only one small point on the vast ocean at any moment, but repeated measurements from many expeditions have built an increasingly detailed picture of the sea beneath its surface. Floating instruments extend these observations far beyond the routes traveled by individual research ships. Thousands of autonomous floats can drift through the oceans, repeatedly sinking into deeper water and later returning toward the surface, while measuring temperature and salinity. When a float reaches the surface, it can transmit its observations before beginning another cycle. Over time, these instruments create profiles from many different regions and depths, providing information about parts of the ocean that would otherwise be difficult and expensive to observe regularly. Because the floats move with currents, they also become part of the water they are studying, traveling through the same circulation that redistributes salt and heat around the planet. Their measurements allow researchers to follow changes in ocean conditions over years and to compare observations from distant basins using a consistent network of instruments. These measurements reveal that salinity can provide clues about changes in the global water cycle. When evaporation removes water from the ocean, surface salinity can increase. When heavy rainfall adds fresh water, salinity can decrease. Melting ice and river runoff can also freshen particular regions, while freezing sea ice can leave surrounding seawater saltier. By observing where the ocean is becoming relatively saltier or fresher over time, scientists can learn something about changes in the movement of water between the ocean, atmosphere, land, and ice. Salinity is therefore more than a measurement of how much salt happens to be dissolved in a particular sample. It can act as a record of processes occurring throughout Earth's climate system. A change measured in seawater may reflect rainfall occurring thousands of miles across an ocean basin, changes in evaporation under warmer conditions, or fresh water entering the sea from melting ice. Climate change is altering some patterns of ocean salinity, although the changes are not identical everywhere. As the climate warms, evaporation, precipitation, melting ice, river flow, and ocean circulation can all change in ways that influence how fresh water is distributed around the planet. Some regions may become saltier as evaporation increases or rainfall patterns shift, while other regions may become fresher because of increased precipitation, ice melt, or changes in the movement of water. Scientists study these patterns carefully because changes in salinity can provide evidence of an intensifying or shifting water cycle. The important point is not that the entire ocean is simply becoming uniformly saltier or uniformly fresher. Instead, the distribution of salinity is changing in different ways from one region to another, reflecting the complicated movement of water through the climate system. Melting ice adds fresh water to the ocean and can therefore reduce salinity in the regions receiving that water. This is especially important when considering ice that was previously stored on land, such as glaciers and ice sheets. When land ice melts and its water reaches the sea, it adds new fresh water to the ocean. Melting sea ice behaves somewhat differently because it is already floating in the ocean, but since sea ice contains less salt than the seawater from which it formed, its melting can still freshen the surrounding surface water. The effect can be concentrated in particular regions rather than spread evenly throughout the global ocean. Scientists monitor these changes because salinity influences seawater density, and density helps determine how water mixes and moves. Changes in salinity can therefore affect ocean circulation. In regions where surface water becomes colder or saltier, it can become dense enough to sink, contributing to the formation of deep water. If the balance of temperature and salinity changes, the density of that water can change as well. Scientists are particularly interested in high-latitude regions where fresh water from rainfall, rivers, melting ice, and ocean transport interacts with cold seawater. The relationship is complicated because circulation is controlled by many factors, including winds, temperature, salinity, the rotation of Earth, and the shape of ocean basins. A change in salinity does not automatically produce one simple outcome, but it can alter an important part of the density structure that helps organize the movement of water through the ocean. Ocean circulation patterns have changed many times during Earth's history. Geological evidence and climate records show that the ocean has not always moved exactly as it does today. Continents have occupied different positions, ocean gateways have opened and closed, ice sheets have expanded and retreated, and global temperatures have shifted dramatically. Each of these changes could alter the pathways available to currents and the differences in temperature and salinity that help drive them. During colder periods, changes in ice formation and melting could affect the supply of fresh water to the sea. During warmer periods, rainfall and evaporation patterns could shift. The circulation we observe today is therefore one chapter in a much longer history of changing oceans. Ancient climate shifts can be recorded in ocean sediments, providing scientists with evidence from times long before direct measurements existed. Layer after layer of material accumulates on parts of the seafloor, preserving tiny remains of organisms, mineral particles, chemical signals, and other clues about the environment in which those sediments formed. Researchers can collect long cores from the ocean floor and study these layers, much as historians might examine pages in an ancient archive. The chemistry of microscopic shells can reveal information about past ocean temperatures and ice volume. The types of organisms preserved in different layers can indicate changes in environmental conditions, while dust and other particles may record changes occurring on distant continents. These sediments allow scientists to reconstruct portions of ocean and climate history, extending far beyond the few centuries during which humans have been able to make precise scientific observations. The ocean floor therefore preserves a remarkable record of Earth's past. Sediments accumulating quietly in deep water can contain evidence of changing climates, shifting currents, volcanic eruptions, biological changes, and material carried from land. Some layers accumulate so slowly that a small thickness can represent thousands of years. Elsewhere, sedimentation occurs much more rapidly. By determining the age of different layers and analyzing what they contain, scientists can piece together sequences of environmental change across enormous spans of time. The salty ocean above those sediments is constantly moving, but the material settling beneath it can preserve traces of conditions that disappeared long ago. And those records have helped reveal that the chemistry of the ocean itself has not remained perfectly unchanged throughout Earth's history. The amount and mixture of dissolved substances in ancient seas evolved along with the atmosphere, continents, climate, geological activity, and life. The chemistry of the ocean has changed throughout Earth's history, just as the planet itself has changed. The earliest seas did not necessarily contain dissolved substances in exactly the same proportions found in seawater today. Continents grew and moved, volcanic activity changed, new ocean crust formed, and old crust disappeared into Earth's interior, while rivers continually carried material from the land toward the sea. Life also became increasingly important. Organisms began using substances dissolved in seawater, incorporating minerals into shells and skeletons, altering the cycling of carbon, oxygen, sulfur, and other elements, and eventually transforming the chemistry of both the oceans and atmosphere. Across billions of years, all of these processes interacted. The modern ocean is therefore not simply an ancient body of water that has remained chemically unchanged since the first rain fell upon the young Earth. It is the present form of a system that has been evolving almost from the moment liquid water became a lasting feature of our planet. Scientists can find clues to those ancient oceans in some surprisingly small places. Tiny pockets of fluid can become trapped inside minerals as crystals form, preserving microscopic samples of the liquids that surrounded them. These fluid inclusions can sometimes survive for extraordinary lengths of time, sealed inside solid material and protected from the changing world outside. By studying their chemistry, researchers can gain clues about the composition of ancient fluids and the environments in which the minerals formed. Other evidence comes from sedimentary rocks, evaporite deposits, fossils, and the chemical signatures preserved within ancient minerals. No single sample can tell us everything about an ocean that disappeared billions of years ago, but many different clues can be combined to reconstruct parts of its history. It is remarkable to imagine that a crystal small enough to hold between 2 fingers may contain evidence of water that existed when the continents, atmosphere, and living world were profoundly different from those surrounding us now. Fossils provide another way to investigate ancient ocean conditions. Marine organisms build shells and skeletons using materials available in the water around them, and some of those hard structures can become preserved after the organisms die. Their chemistry may reflect aspects of the seawater in which they lived. By examining the proportions of particular elements and isotopes within fossil material, scientists can infer information about past temperatures and changes in ocean chemistry. The organisms themselves also provide clues. Different species thrive under different environmental conditions, so changes in the types of fossils found within layers of sediment can reveal changes in temperature, oxygen, depth, and other characteristics of ancient seas. A microscopic shell buried in mud millions of years ago can therefore become a record of an ocean that no longer exists in exactly the same form. Salt deposits preserve another chapter of that history. When ancient seas or lakes became isolated and evaporation removed large amounts of water, dissolved minerals could become concentrated enough to crystallize. Layers of salt accumulated on the bottom and were sometimes buried beneath later sediments, preserving evidence of vanished bodies of water. Geologists can study the minerals within these deposits to learn about the chemistry and environmental conditions that existed when they formed. Different minerals crystallize under different conditions and at different stages of evaporation, allowing a thick sequence of deposits to preserve clues about how an ancient basin changed as its water disappeared. Some of the salt mined far inland today therefore carries information from a sea that vanished millions of years before the first human beings appeared. These records also show that ocean salinity has varied over geological time. The oceans have remained salty for an extraordinarily long period, but that does not mean their average salinity has always been exactly 35 parts per thousand. Changes in the amount of water stored in ice, the movement and weathering of continents, volcanic and hydrothermal activity, the creation and destruction of ocean basins, and the formation of large salt deposits can all influence the long-term balance of dissolved substances in seawater. During periods when enormous quantities of water became locked into continental ice sheets, for example, the remaining ocean could become somewhat saltier because water had been removed, while much of the ocean's dissolved salt remained behind. When large ice sheets later melted, fresh water returned to the sea. Over still longer periods, geological processes could remove salts into sediments and rocks or return dissolved material to the ocean. Continental movement has played an important role in these changes because the positions of land and sea determine how water circulates and where evaporation, rainfall, weathering, and sedimentation occur. When continents collide, mountain ranges can rise and expose fresh rock to weathering. When continents separate, new ocean basins can open and new seafloor can form. Narrow connections between seas can open or close, changing the movement of water between basins. A sea that becomes partly isolated in a dry climate may lose enormous quantities of water through evaporation, allowing thick salt deposits to form. Millions of years later, tectonic movement may lift those deposits above sea level or bury them beneath younger rock. The salt can then become part of the continents once again, waiting until erosion, groundwater, mining, or another geological process moves it somewhere new. The rise and erosion of mountains can alter the amount of mineral material delivered to the sea. Newly exposed rock provides fresh surfaces for rainwater and chemical weathering to attack. Streams flowing down steep slopes carry sediment and dissolved ions into larger rivers, which eventually transport part of that material toward the coast. As mountains slowly wear down, the products of their erosion can travel hundreds or thousands of miles from the places where the rock originally formed. Some particles settle along the way, while dissolved substances remain within the moving water. A mineral raised high above sea level by tectonic forces can therefore begin a long journey downward through the landscape until some of its chemical components eventually reach the ocean. Geological uplift and erosion become another part of the immense recycling system connecting Earth's interior, continents, rivers, and seas. Volcanic activity has also varied throughout Earth's history, altering the exchange of gases and minerals between the planet's interior and its surface. Volcanoes release water vapor, carbon dioxide, sulfur compounds, chlorine-containing compounds, and other materials, while volcanic rock exposed at the surface can later undergo weathering. Beneath the oceans, volcanic activity and hydrothermal circulation continue changing the chemistry of seawater and oceanic crust. When the rate or location of volcanic activity changes over geological time, the movement of chemical substances through the Earth system can change with it. The young planet we visited at the beginning of our journey was far more volcanically active than the world we know today, yet the connection between Earth's interior and its oceans never completely disappeared. It continues quietly beneath the waves. Even with modern instruments, however, many details of the ancient ocean remain uncertain. Scientists can reconstruct portions of its history from rocks, minerals, fossils, sediments, and chemical evidence. But the oldest chapters are particularly difficult because Earth's surface continually destroys and recycles its own records. Oceanic crust is created and eventually returned to the mantle. Sediments are buried and altered. Mountains rise and erode, and rocks can be transformed by heat and pressure. The farther backward we travel, the fewer direct records remain. This means that questions about the exact chemistry of the earliest oceans continue to be investigated. New discoveries can refine earlier ideas, and new techniques can reveal information from materials that once seemed almost silent about the distant past. Modern ocean exploration continues this search for understanding. Research ships cross the seas collecting water and sediment samples. Instruments descend through thousands of meters of water to measure temperature, salinity, oxygen, pressure, and other properties. Autonomous floats travel through currents and return observations from remote regions. Satellites watch the ocean surface from space, while remotely operated vehicles and other machines descend into places where sunlight has never reached. Scientists investigate hydrothermal vents, deep trenches, underwater volcanoes, sediments, currents, and marine ecosystems, continually adding detail to our understanding of how the ocean works. The sea covers most of our planet, yet much of its deepest environment remains difficult to observe directly. Every new measurement helps fill another small part of an enormous picture, and throughout all of this exploration, the chemistry of seawater remains one of the clues connecting the ocean's present to its ancient past. The salt in the sea is not there because of one event, one river, or one source. It is the result of a planetary process that has continued across billions of years. Water vapor gathered in the atmosphere of the young Earth and eventually condensed as the planet cooled. Rain fell upon exposed rock. Carbon dioxide dissolved into that rain and helped make it slightly acidic. Chemical weathering released ions from minerals. Streams and rivers carried those dissolved substances toward the ocean, while volcanoes and interactions with the oceanic crust contributed additional material. Water evaporated from the sea and returned to the atmosphere, leaving most dissolved salts behind. Meanwhile, organisms, sediments, chemical reactions, hydrothermal systems, and geological processes continually removed other materials from seawater. This is why the ocean can remain salty without simply becoming saltier forever. It is not a container that has been filling without limit since the beginning of time. It is part of a vast exchange system. Salt enters, salt leaves, water moves, rocks weather, sediments form, crust is created and recycled, and life continually participates in the chemistry of the sea. The balance has changed during Earth's history and will continue changing in the future, but the ocean we know today represents the combined result of all of these processes operating together. So the next time you stand beside the sea and taste a trace of salt carried through the air, there is an extraordinary history hidden within something that seems completely ordinary. Some of the ingredients dissolved in that water began their journey within rocks. Rain helped release them. Rivers carried them. Geological processes moved them through the planet, while currents carried them through the sea. The water surrounding them may have evaporated into clouds and returned as rain countless times, while the dissolved substances followed much slower pathways through oceans, sediments, living organisms, and stone. A single drop of seawater therefore carries a connection to an Earth far older than any landscape we can see around us. It connects the rain falling on distant mountains with rivers flowing toward the coast. It connects volcanoes beneath the sea with minerals locked inside continents. It connects microscopic plankton with coral reefs, deep ocean currents with polar ice, and ancient salt deposits with oceans that vanished millions of years ago. What began as one simple question has carried us through almost the entire history of the planet. Why is the ocean salty? Because Earth is constantly changing, and water is one of the great travelers through that changing world. For billions of years, it has moved through the atmosphere, across stone, along rivers, through the ocean, and back into the sky. Along the way, it has dissolved, transported, concentrated, exchanged, and left behind the minerals that give the sea its familiar taste. The saltiness of the ocean is not merely a property of water, it is part of the record of a planet shaped by rain, rock, heat, life, and time. And perhaps that is the most peaceful thought with which to leave our journey tonight. Beyond the shore, the ocean continues moving, as it has for an almost unimaginable span of time. Rivers continue arriving, clouds continue forming, rain continues falling onto mountains. Deep beneath the waves, seawater continues passing through the rocky crust, while far above it, water rises silently into the atmosphere and begins another journey around the planet. The cycle continues, whether anyone is watching it or not, connecting the sea, the sky, and the land in a process older than almost everything familiar to us. And within that immense and patient cycle lies the answer to the question that began our story, written quietly into every salty drop of the sea. And as our journey through the oceans comes to an end, you can rest knowing that even something as familiar as the taste of seawater carries a story billions of years in the making. From ancient rain falling on newly formed rock to rivers carrying minerals toward the sea, the salt in our oceans is part of a cycle that continues quietly around us today. I hope you enjoyed learning why the ocean is salty. Sleep tight.